Hi all, this video is about the memory consistency models in distributed shared memory. So here I am going to explain about the different consistency models. So before that, let us discuss about the notations used for various operations. So you have basically read and write operations. So here the first notation is write x comma a. So which means you are going to write the value of a to x. Okay, and another operation you have is read of x comma a. So which means variable x that returns the value of a. Okay, so that's a meaning. So now basically when if you have the subscript value subscript some I denoted with the with respect to the operations handled, so this I represents the processor involved in doing that particular operation. So this is a basic notation, write and read. So having said about this notation, let us see about the first consistency model. So that is a strict consistency model. It is also called as atomic consistency or linearizability. Okay, so that is the model about. So let us see what is this. So this is a most stringent model where you have to have the sequential and the linearizable, both the properties to be satisfied. So let us see in detail how is this going to work. So basically now we are going to assume that we have two features. Assume two features, right? The one is the availability of common one is the availability of common global clock. Okay, so we are assuming that it is available in a uniprocessor system. And the second one is whenever you perform a write, it is immediately visible, right? So write operations are visible to all processes immediately. Okay, so these are the features of the system, that is the strict consistency model or atomic or linearizability, right? So why is this called as an atomic in the sense that there is no other interference. If once the operation is invoked, you will get the response without any interleaving of other operations. So you feel that it is done uh, together, right? So without any intervention of the other processes. So that is about the atomic consistency model. So these are the salient features. Now so here the model that we can explain, the basic model used in this strict consistency is, you can see if you have a read to any location. Okay, so if you're performing a read operation, it should return a recently returned value. Okay, so that means the first thing that you have to take care is reads should return the most recently write to the location. Okay, say if a read operation is done on x, so if x is recently returned with an updated value, that updated value has to be returned by the read operation. Okay, so here you can see the reference of the global time, because in case in this distributed shared memory, there is a risk of you have to understand whether the data is replicated, whether you have an interleaving of operations with other processes. So you will be having more concurrent accesses, and the multiple replicas will be managed, right? So in that case it is going to be very difficult to get this kind of action. So that's why this is kind of a strict consistency model. We have to ensure that all the replicas are correctly done, and it should ensure that the program order is not changing. So that's why the sequential plus the linearizability action is togetherly combined here with reference to a global time, right? So you are referring to a global time axis. So based on that, this most recently is given the notion of time. Okay, so that is there. Most recently return value should be read by the process. Okay, so so if the operations are not overlapping, then with the help of this global time references, you will be clearly able to identify which action has taken first, which action has come next. So with that, you will be able to identify if the set of operations are not overlapping. But if they are overlapping, then you may have to understand the different possibilities. So before I go to that, let me explain what is non-overlapping and overlapping actions. So you can see here in this example, here I have, say I have here okay, say right of x comma a. Okay, and here I have read of x comma a, and here also I have read of x comma a. When you can see here, none of them are overlapping. If this is represented as a time, increasing timestamp, you can see that none of the events, the program order is not overlapping with each other. So this is a non-overlapping operations. So here you can see the time base is clear, and you can clearly cut where the event has happened without any overlapping. So now, so if you can see a next example, let us see an example for overlapping case. Say you have write okay, so you have here write of x comma a. Next I have here a read you have so here I am reading x comma a. Here also I am reading x comma a. Here I am reading x comma a, and here I am writing I comma a. Okay, so you can see you cannot cut the clear boundaries because now this action is actually an overlapping set of operations. So we should be clear which write is value is read by which read operations, right? So this is a set of overlapping operations and this is a set of non-overlapping operations. Okay, so hope that part is done. Now coming back to our, so that's why this is kind of an strict, because if there is an non-overlapping case, then with the reference to the global time it will be able we will be able to easily identify which is the most recently returned value, right? So but if it is an overlapping operations, then we may have to clearly specify what is the rule that we are going to use. So let us see that now if the operations are overlapping. Okay, so I'll just write here overlapping. If the operations are overlapping, what you have to do, we have to ensure that all operations uh, appear to be executed atomically and sequentially. So as I told, there should not be any interleaving. So operations all operations appear to be executed atomically and sequentially. Okay, so that is if the case is overlapping. Also one more necessary rule is there, so which is you have to say multiple processors are involved, right? So all processors have to see the events in the same order. Okay, all the processors should see the events in the same order, that is same ordering of events. Okay, so what do you mean by same ordering of events? If it was not an overlapping kind of operation, you can clearly specify the sequential, the program order the operation is executed. So when you identify an overlapping, it's a kind of an overlapping set of events. So we should be in a position to identify equivalent non-overlapping set of events with respect to the global reference time. Okay, so those are the two necessary specifications required if the events are overlapping. If the events is not overlapping, we are very clear that this every read should be reading the most recently returned value, right? So that is the idea. Now coming to the next point, that is linearizability. So when can you tell that the set of operations are linearizable, or you call that as a strict consistency model? So we have seen the sequential part where the program order is more important. Now whether we are able to linearize it or not. Okay, so sequential plus linearizability is the strict consistency model. So what are the rules behind the linearizability, or how you can tell that the given set of actions or the given set of events that is occurring in the process is linearizable or strict consistency model or not? Okay, so the first of all we you have to understand that you have set of events occurring and you will be denoting it as a sequence, so seq. So seq will be is actually the collection of events. Okay. Okay, so SEQ, you will be having set of events occurring with respect to the global order. Okay, so if I can tell that if I can find any SEQ, any permuted, I will tell permuted SEQ, okay, which is similar to this set of events, even if it is not in the correct order, any permutation of SEQ which leads to the same semantics as what is there in the original, then you call this as linearizability. Okay, so without any change in the meaning or any change in the final output, if I can find any other permuted sequence, then I call that set of events as linearizable. Okay, so if there is a permutation, say for example permuted SEQ, I label this permuted SEQ as some SEQ prime. So if you have this kind of action, so you know every event is denoted with two actions, that is you will be invoking the event and you will get the response, right? So these are the event. So if it is satisfying this property, then you call it as linearizable. So what are the properties? First property is you have for every variable, say you have a variable v. Okay, so any variable v, so if you can find the SEQ cap, the projection of SEQ cap on SEQ prime on v is denoted by, say for example this is denoted by SEQ prime v. Okay, so this particular variable v, okay, and you have a permuted combination of events, that is SEQ prime. So if I am projecting all the operations which I have identified in sequence prime on this variable v, right, in such a way that every read returns the most recent write, okay, that immediately precedes it. Okay, that's the first condition. So consider a variable v, and if I have identified a permuted sequence of the original sequence, and I'll try to project this set of events on v, so that is denoted by SEQ prime v. So here every read, so if variable v is read, so every read returns the most recent most recent write. Okay, so that was immediately preceded by this action. Okay, so every read of that particular variable v should return the most recent write. So that is the first rule. And the second one is, say as I told, every event or every operation is associated with the invocation of that operation and the response that you got from that operation, right? So now for example, so if I have an operation called OP1 and I am getting the response of that, okay, so the response of operation 1 you should get that response before the invocation of operation 2, right? So I'll just denote it with an arrow. So this arrow represents that it proceeds. The operation 1's response is you're getting it before the invocation of operation 2. I'm just writing this as invocation. Okay, so in the sequence, so then you can tell that operation 1 occurs before operation 2, because so if I have an operation 1, so this will be invoked, right? So you will be having invocation step, it executes and it returns the response, right? Then you will have operation 2, it invokes, so invokes the operation, either it can be read or write, right? And it gets the response. So what is the action? So any sequence here, you can see the when you if you're trying to invoke another operation, the response of that particular operation before it was invoked should be executed, right? So which ensures the order in which the operation needs to be performed. So these are the two conditions for checking the linearizability of the given events. Okay, so based on that, let us see this example. So in this example, you can see the different actions. You can see sequentially consistent but not linearizable, right? So what are based on the conditions that we have discussed. So here you can see write x4, but what you are reading here, you can see here, I'll just mark it in red color. Here you can see that read x0. So I processor 1 is writing the value of 4 in variable x. Okay, whereas after this action you can see the read x comma 0, right? It is assuming that the initial value of x. So here assumption is initial value is 0 for the variables. Okay, so here you can see as per our definition, every read which happens which happens after some write should read the recent return value, right? But here you can see x is successfully returned after this position x. Wherever you are reading x, it should return the value of 4, but it is reading 0. Okay, but whereas this action is correct. You can see processor 2 writes a value of y and processor 1 reads the value of y correctly, but this is not there. So here you can tell that based on this, you can see that the event is not linearizable, because you can see read by p2 begins after write. Write is not reading the recently written value. Okay, so this you can see the order, event order is not correctly satisfying. So this action, this is not linearizable. Now let us see the next one. You can see here read x by 4, write x of 4, that is the p1 writes the value 4 to x, and you can see the read which is happening after, or it's a kind of an overlapping, but it is after writing. So here you can see that read is successfully done and the same action. So here it is sequentially consistent and linearizable. And in this you can see here write of x comma 4, it reads x comma c, y 2 it reads 0, right? So both of them are not consistent, sequentially consistent, and hence it is not linearizable. Okay, so these are the examples of checking the linearizability. And the algorithm here, you can see you will be having a shared variable x. So when the memory manager receives a read or write Okay, so read or write from any application, what is action taken. You can see the total order broadcast the read or write request to all the processors, right? So the processor which is trying to invoke the read or write operation will broadcast it to all the processors. Okay, it is a total order. Then it awaits for its own result to reach back, await own request that was broadcast. Then meanwhile when it is waiting, it is just perform pending response to the applications as follows. So if it was a read, then a return value from local replica, right? Case write to local replica and return acknowledgement to application. Okay, so this action is taken when it is awaiting for its own broadcast message to receive. So it will, when it is waiting, it gives responses to the pending. So if it is a read action, it reads a value from the local replica. If it is a write, it returns back the updates the local replica and sends the acknowledgement. Now, for example, once it receives, okay, so this part is to receive the write. Okay, so here the broadcast action is done. So now it receives, a memory manager receives a particular request, that is a write. So write x comma val from the network x, networks. So write the value to local replica of x. So what is it it is doing? So when it is a write request, so it will be writing the value to the local replica. And here the next step is for the read action. So when you perform a read, there is no operation done. Okay, it is just included in the total order because we have to maintain the set of operations, right? We are maintaining the sequence, right? So in this sequence we need not miss any of the events that is happening, that is write or read. Even though there is no operation, it is just copying the value from the local variable, no updates or nothing is done. But since this is a kind of a total order, we are going to keep track of all the events that is happening, and that's how the linearizability can be implemented.